Hi everyone, my name is Juan Linde Domingo, and I would like to share the progress in a project I've been working lately as a postdoc together with my supervisor, Bernard Spitzer. In this project, we studied the geometry of gaze pattern during cued working memory maintenance of visual object orientation. For that, 29 participants took part in a task where two objects were sequentially presented with a random orientation. Right after, an auditory retro cue here indicated which orientation will be tested after a delay of 3.5 seconds. At the test, participants were asked to press a key to rotate the cue object to its original orientation. In half of the trial, after the test, the remaining item was cued and tested after a second delay. With this setup, one orientation is assumed to be in the focus of attention during delay 1, while the other is assumed to be temporarily unattended. This heat map shows participants' eye position on a scale with the actual object side during the delay period. Here, we offline re-rotated the gaze to realign them with the object upright position. As you can see, participants seem to follow our instruction and fixate it quite well. Any eye movement were quite small, around 0.3 degrees visual angle relative to object side. And this pattern was seen in all objects used. In order to test if there was still orientation information hidden in this small eye movement, we used representational similarity analysis in gaze space. What we did is calculate the Euclidean distance between all orientation and create a representational dissimilarity matrix. This circular orientation model was then correlated with the gaze data at every time point of the experiment. In this figure, you can see the correlation between the data and the orientation model on the y-axis, with time on the x-axis. During item presentation, we found clear evidence of orientation encoding in gaze for the first object, in blue lines, and the second object too, the greenish line. Interestingly, we found that after the retro cue, participant gaze clearly maintained information about the cue orientation, and this ramped up throughout the delay period. However, the representation of the on-cue orientation dropped to baseline, even though the on-cue item would be later tested in half of the trial. We applied the same approach also to EEG signal, which was recorded with another group of participants who showed the same eye movement pattern. Although the orientation information was reflected in ERP pattern during encoding, we did not find robust evidence of sustained representation during the delay period. Similarly, we did not find any evidence for the orientation information being reflected in alpha power. In other words, the small eye gaze pattern reflected information that was invisible to our EEG analysis. One important aspect of our paradigm is that we use different objects. This allows us to investigate the extent to which the orientation information in eyes is object independent, that is generalized or abstract, or carries concrete object-specific visual information. We again use our RSA approach, but now we calculated the distance structure within object, the group in the diagonal, and between objects. This way, we can separate object-specific and generalized orientation information. If we take a look at the orientation representation of the first item during the first retention period, we can see that object-specific and object-independent are almost equally strong. This suggests that the orientation information is full generalized and object-independent. However, there is one exception to this, when the second object, the just seen object, is cued to be maintained in delay 1. In this case, we found a significantly stronger representation of object-specific information, which point to a more concrete visual content in working memory for just seen information. During the second delay then, however, the orientation representation of both items was fully object-independent, suggesting that temporary inattention rendered the working memory representation more generalized or abstract. In a still ongoing analysis, we are also inspecting the data with respect to orientation biases, specifically cardinal bias. With our RSA-based approach, we can quantify cardinal bias through a mixture or a perfectly circular orientation model, no bias, and a square model, which will reflect maximal cardinal bias. We quantify this mixture with the parameter A, which ranges from 0, no bias, to 1, maximum bias. Intermediate values will lead to a spherical representation of the orientation space. Using this approach, we generally find values of A larger than 1 in the A data during the delay period, indicating that the gaze pattern carried cardinal biases early on during working memory retention. We can use the very same model also for our behavioral data. We show clear cardinal biases, which the model explains quite well. This is consistent with early work on cardinal biases in working memory. Now, if we compare the bias pattern in eye during the two delayed periods with the bias in behavior, we find a degree of similarity in results with a stronger bias for the second cued orientations. That is, after the working memory information has been temporarily unattended. However, the eye data additionally indicate again a special status of the just seen item. Its orientation was less biased in the eyes during the first delay, and this effect was also reflected in behavior. So, the preliminary results do indicate a relation between gaze and behavior, which is, however, imperfect and requires further investigation. In summary, our first results indicate that gaze patterns may carry rich information that could be instrumental to understand the formats of working memory content, their temporal dynamic, and also their link to behavior. So that's all. Thank you for your attention, and also thank you to all my colleagues at the Center for Adaptive Rationality.